So last week, we went over the definition of the Laplace transform and the overall idea of the Laplace transform. Today, I want to talk about using Laplace transforms to solve differential equations. The first thing that I need to refer you to is a table in your book. So refer to table 6.2.1, and it's on page 317. And when you're looking at that table, which I assume you are right now, pause the video, go get your textbook, look at the table. What you'll see is basically two columns. On the left, we have the original components of your differential equation, and on the right, you have the Laplace transform. So I want to copy out a few lines of that table now. So, as I said, on the left, you have your functions in your original differential equation. This would be the, say, inverse Laplace transforms of the Laplace transform. And on the right, you have, excuse me, you have your Laplace transform, and that's the Laplace transform of the original. So here we have the original, here we have the Laplace transform. Over here, as I said last week, the variable we're going to use is t in our original differential equation. When we take the Laplace transform, the variable is going to be s. And we tend to use lowercase letters in the original and uppercase letters in the Laplace transform. So a few of these I want to show you. In the first line, if you have a 1, you would have the Laplace transform of 1 is just 1 over s. And we have the restriction that s is greater than 0. You could easily do this the same way we found the Laplace transform of e to the t last time. So remember the definition. You take the integral from 0 to infinity, so on, with using t as your variable of integration. That makes t go away entirely, and you end up with 1 over s, and it only converges, that improper integral only converges if s is greater than 0. So if you have e to the at, we did e to the t last time. If you put in at, you'll see what you get is 1 over s minus a. We did e to the 1t, and we got 1 over s minus 1, and this only works if s is bigger than a. That's the only place it converges. Usually these the place where it converges, the interval convergence, is not going to be such a big deal for you as far as using Laplace transforms. So I want to include a few more lines of this. I'm certainly not going to include it all. Sine at is a over s squared plus a squared. And that again works if s is positive. And line 6 is cosine at. And this is s over s squared plus a squared. Again, where s is greater than 0. And I want to tell you one more line in this table, and that is line 18, where we have the nth derivative. Remember, when you have something that looks like an exponent, but the exponent is in parentheses, it actually means the nth derivative. And this, you have quite a long expression. It says s to the n, and then this is the derivative of f. Sorry, this is the Laplace transform of f, and of course that's of s, minus s to the n minus 1, f of 0, minus s to the n minus 2, f prime of 0, all the way up to s to the n minus n, in other words, s to the 0, the n minus first derivative at 0. So that goes with that, that goes with that, that goes with that, that goes with that, and that goes with that. Let me show you how you would use this last one. Say, if I take the Laplace transform of, let's say, the first derivative. So here, n equals 1. Then according to this rule, what I have is s to the 1, just, in other words, just s, f of s, so capital F of s, the Laplace transform of s, so minus f of 0. So the next one, every time the s goes down in power, we go from s to the 1 to s to the 0, and we have the n minus 1th derivative. So the 1 minus 1th derivative is the 0th derivative, just the original function at 0. That's what this says. If I take the Laplace transform of f double prime of t, here n equals 2. So I start off with an s squared. The first one is always capital F. And remember, capital F is just the Laplace transform of lowercase f. That's basically what it says up here in the title, that capital F is the Laplace transform of lowercase f. So here we have, according to this, s squared f of s minus, now the s's go down by 1, so we have s to the 1, f of 0. So the derivative is going up by 1 every time, minus, now the s's go down to s to the 0, which I don't write, f prime of 0. We went from the 0th derivative to the first derivative. If instead of having like f double prime, I had like y double prime, we're taking the Laplace transform of y double prime, I just replace, wherever I have f's here, I'll replace them with y's. So s squared y of s minus s y of 0 minus s to the 0 y prime of 0. If I wanted the third derivative, so the Laplace, I'm running out of space here, I'm going to erase some of this stuff over here. Oh, maybe that was that move to erase what I had down here, but if I have the, let's say, y triple prime, according to the rule, which I have erased, but it's clearly in your notes, what I have here is s cubed y of s minus s squared s squared y of 0 minus s y prime of 0 minus s to the 0, which is 1, y double prime of 0. Hopefully that's showing up on the screen. If it's not, I will s cubed y of s minus s squared y of 0 minus s y prime of 0 minus y double prime of 0, s to the 0, y double prime of 0.